Hello, everybody. I'm Jansa Genlo, a member of the NASA team for CIOS WGISS. We'd like to welcome you to the first CIOS WGISS Technology Expo webinar. The webinar topic for the day is the relevancy ranking of data search results. And our first speaker, Chris Linus from the NASA WGISS team, he has been leading the research in this area for NASA for quite some time. Chris?
Thanks, Jansa. Can you all hear me? I'm going to talk today about, this is actually a bit of a reprise of a talk that I gave at HGU to introduce this same subject. And I've called this relevancy ranking of satellite data search results. Often I'll just abbreviate it as search relevancy. And this seemed a particularly apropos topic for WGISS because, WGISS is this fairly large group of multiple organizations, all with their own holdings, with their own search interfaces, et cetera. And in fact, we actually had Stefano Nativi give a talk to one of our working groups on search relevancy, and we'll hear some of that work a little bit later after my talk and James's talk. So this actually came out of some talks that I was giving to, I guess I'd call it the big data community. And they have this catchy thing with the V's. Sometimes there's 3 V's, volume, variety, velocity. Sometimes there's as many as 7 or 8 V's. The particular V that causes us some trouble here is what they call the variety problem. And what I'm going to talk about is where this comes from with respect to satellite data in particular. So, normally you would think that variety equals choice, and choice equals good, right? So variety must be good. And generally speaking, that's the case, but I'm going to go on to show you why it also provides us with a bit of a challenge when it comes to serving our users. And my particular system is the Earth Observing System Data and Information System. It's the last time you'll hear me spell all that out. I'm going to call it EOSDIS from now on. And this is a very simple context diagram of where EOSDIS sits in the scheme of things. The data is downlinked from our satellites, it's captured and cleaned. We often process it to higher levels of processing, which I'll come to in a couple of slides. Then we archive and distribute it to a variety of user communities, research, applications, and education. And here's where the variety problem comes into being, is it turns out that when you do all of that processing and archive and distribution, you actually end up with a lot of different science products that are of interest to those end users. And in this case, I'm showing the trend over time of the different science products, sometimes we call them data sets. So I'm not talking about individual files here, but these are data collections. The number of different data collections distributed out to our user community. And you can see, for one thing, the number, and this is only as of 2015, the number is fairly high, 3,700 different data sets. But perhaps more alarming, I guess, is that graph is going up and still going up. And so it indicates that variety problem is with us to stay. So, of course, I mentioned we have a distribution system. With so many data products, we've got to have a fairly robust search interface. This is our most recent search interface called Earth Data Search. It gives you a little idea of the splash page. And when I go to the next screen, you'll see where this variety problem comes into play. So typed in ozone here, and we get 1,084 matching collections. If you do this today, that number might very well be different because those collections change over time. And 1,084 collections is just too many to go through manually. There has to be some kind of machine help for end users to be able to find the data sets that are most used to them. And it helps to know where this variety comes from. So we've got variety with our number of instruments. And instrument variety both comes from cases where you've got fundamental differences between instruments, say a sounder, a limb sounder, an imager, radar, but also cases, and this happens a lot within NASA, where we're going through incremental evolution and instrument design. In fact, we're more about sending up instruments for research purposes, and so it's very common for us to make each instrument better, but also different from its predecessors. We also occasionally will fly the same instruments on different satellites, Even in those cases, though, the instrument is never truly exactly the same. There's a little bit more optical crosstalk on one than the other. I mentioned processing levels. So we start off with calibrated data, and then we retrieve geophysical parameters at the SWOT level. Then we often grid that into a regular grid, and that often goes into a model, particularly a data simulation. Different processing algorithms are often used, even to extract the same geophysical retrieval. This is the case with the ozone monitoring instrument, for instance, where there are two completely separate algorithms for deriving ozone. But you also have cases where, again, we're doing that incremental evolution in algorithm development. And then when we get to the gridded point, we also often aggregate the data to different time resolutions. So we'll start off with daily, but for some of the products, it's useful to have a 5-day product or an 8-day product, and we'll usually also have a monthly product as well. And then spatial resolution can also be different. Here's a quick example of a time aggregation issue. This is for the multi-angle imaging spectroradiometer, also known as MISR. And it has a fairly narrow track. So if you look at a daily product, the usefulness of that product for your particular uses is likely quite different than if you look at that monthly product. But on the other hand, it doesn't mean that the monthly product is the best product for everybody, because it shows some peculiar artifacts having to do with that daily those daily gaps. All right, so what do we do? Well, what we'd like to do is to emulate the best search engines, and what they try to do is return the most relevant results at the top of the list. So if we look at Wikipedia on what the definition of relevance is, it's how well a retrieved document or set of documents meets the information need of the user. And I've underlined information need because I'm going to come to that actually in the final set of talks where we start to look towards the future. But note that we are looking to get something that's relevant to that particular user whenever possible. So how do we do this? Well, first we've started off by developing some basic relevancy ranking heuristics. For heuristic, it's really just a rule of thumb. And you might ask what the basis is. Well, the basis is we've been doing this for 20 years, so we ought to have some idea of what makes a good data product for the end user community. We've had a lot of interaction with them at science meetings, through our help desk, through their meetings, and so we have some idea, also by looking at the research articles that are written from the data, we've got some idea of what kinds of data are applicable to what sorts of uses. So the beginning, the most obvious one, I think, is what I call the content heuristic. And the content heuristic, for instance, if I type in ozone, chances are very high that what I want is a data set that has ozone in it. I mean, this is not necessarily a foregone conclusion. For instance, you can imagine that instruments are named after ozone, like the ozone monitoring instrument, but a data product has some other species, say sulfur dioxide, then it's possible that there isn't ozone in that particular case. So we do have to take a little bit of extra care to make sure that if we put in something that represents data content, that we're going to get data sets up at the top that have that content in it. So that's a fairly simple one. Now let's go on to the next step, and these are what I call new and improved heuristics. And this, again, goes back to that continual evolution that we try to do at NASA with respect to both the instruments and the algorithms that are retrieving geophysical parameters from those. So for instance, I mentioned that we're constantly improving those algorithms, and from that we can infer that the later or the higher the version of the algorithm, the more, what's the word I want, the more accurate, the better quality that higher version is likely to be, and therefore the more likely it is to be useful to the end user. Now there's a side benefit that comes out of this as well, which is that once we have a better version of the algorithm, we stop using the older version to process the data. We'll often have maybe a 6-month, maybe a year overlap just for comparison purposes. But once we've really decided that we've had enough overlap and that new version is definitely better, then we essentially stop processing the old version, which means if you're looking for more recent data, it's only going to be available in the most recent version of the algorithm. And I mentioned the part about the newer instrument is usually better than previous instruments. And so here's a good case of that. We've got the total ozone mapping spectrometer. This is an instrument of vintage 90s, early 2000s. It was followed on by the ozone monitoring instruments, OMI, which was launched in 2004 on our Aura satellite. And there actually is some overlap between, the latter years of TOMS and the early years of OMI. And here, in fact, I'm showing a particular day where those do overlap. And you can see that one of the major improvements that we've made in the ozone monitoring instrument is the fact that we've got much higher spatial resolution, that same blockiness that you see in the total ozone mapping spectrometer. Another thing that you can see is that there are a few places where you can actually see, let me try the pointer here. So there's a few places, like down here, where we were actually unable to retrieve data for that space for the total ozone mapping spectrometer. But on the other hand, when we look at the ozone monitoring instrument, the more recent experiment, we are able to retrieve values for that particular spot. Now, the next category of things I'm going to look at is what I call the region of interest overlap. And the region of interest overlap actually applies to two different kinds of regions. The first region is that region in time. So this is what called the time range heuristic. This is a fairly simple one. It's basically saying the data sets that cover the user's full time range. In this case, let's say the users put in 2005 through the middle of 2009. If I look at just the TOMS Earth probe, I only have overlap for 1 6-month period there, whereas the ozone monitoring instrument would cover the entire time period. So in this case, we want to show the data sets coming from the ozone monitoring instrument above those coming from the TOMS Earth probe. Now, the second kind of region is the spatial heuristic. And so again, we go by the premise that data covering the user's full area are better than those covering just part of it. So if we look at this case where the search region and the spatial region of the data set are just partially overlapping, we go to the next case where the entire user region is covered by that spatial region of the data set. This obviously is going to be of more use, all other things being equal, than that previous case would have been. And so those are the basic heuristics that we've been implementing to date. We're going to come back at the end of this discussion, and I'll show you some of the things that we're looking forward to that are beginning to bring the user more into the picture. Yantuk?
Yes. If you have any questions, please type them into the Q&A block, and we will have a question and answer session at the end of all the presentations. Our next presentation is from James Norton, who is with the NASA Heuristics team. James?
Hi, my name is James Norton, and I'm one of the developers of the Common Metadata Repository. I'm going to talk to you today about some of the changes we made to the Earth Data Search client and to the CMR to improve relevancy. First of all, what is Earth Data Search and Earth Data Search client? Earth Data Search is a client application that allows you to search science data using a combination of keyword searches, temporal searches, and geographic searches. It provides a faceted hierarchical search result that's backed by the Common Metadata Repository, which is the system that provides a REST API for searching through the metadata. And this is basically the interface to Earth Data Search. Okay, so why are we concerned about search relevance? Chris talked a little bit about this, but basically in 2015 and leading up to that, our catalog grew substantially. And so now we have about 4 or 5 times as much data as we had before. And so as our data grew, so did our relevancy needs. Now searchers could bring back thousands or even tens of thousands of results, and it's just intractable for the user to search through each one of those, through that long list and come up with the data that they actually want. I mentioned the Earth Data Search faceted result list, which basically is a hierarchical representation of all the results that have come back in categories that are dynamically generated. The problem is that when you have tens of thousands of results coming back, entire categories can get buried in the results from other categories. So in this case, we see a user did a search and you got some Landsat categories that came back, but you don't see Landsat 8 here. So that leads to the question that users can be confused because they don't know if we just don't offer Landsat 8 or if what really happened here is that it just got buried by the results from all the other categories. Also, we found that we were getting feedback from users that echo the need for better relevance. We had questionnaires and different feedback mechanisms for users, and we were constantly seeing a request for better, more relevant. Basically, the bottom line is that if users can't find what they're looking for, none of the other work matters. It doesn't matter how fast the CMR is. It doesn't matter how elegant the user interface is on Earth Data Search. If people can't find what they need, then we're not delivering what they want. In addition to just pure relevancy problems, there are issues with the challenges beyond relevance. Well, the first issue we have is that metadata is just in generally imperfect. We have issues where there are inconsistencies in labeling. You see on the left here, we have, let me see if I can find the pointer. On the left here, we have, that's really delayed. All right, never mind the pointer. On the left here, we have different ways of labeling different levels. So we have level 1, we have 1, 1A, and those kind of inconsistencies show up in the facets. We also have misspellings in the metadata, so you have biosphere here as well as biosphere. And this can generally lead to problems where you have more facets than you actually intend. All right, so what have we done to try and address some of these problems? Chris talked about some of the ideas, but what have we actually done? Well, one thing we've done is that we've improved things not only on the front end, but also in the core capabilities on the CMR. The first thing we did was implement or improve relevancy with regard to temporal searches. So now we actually provide a relevancy score based on the percentage of temporal overlap. So the more that a collection overlaps the temporal range that you selected in Earth Data Search, the higher it's going to show up in a list. Next, sorry, let me go back here. All right, the next improvement that we implemented was a community usage metric. Estes collects, through the Estes metric system, collects data about all of its holdings. And so we can access data to for the collections. How many times have each collection been actually downloaded by someone or obtained by someone? So we use that to generate a community usage score, and that's computed and indexed with the collections. So then we can apply that as a subsort for relevancy when people do keyword searches or temporal searches or any other kind of search. We can subsort based on this community usage metrics. And so this basically lets things that are popular show up higher in the, or I should say, have a higher community usage show up higher in the list. The other, one of the other improvements we implemented that Chris had talked about was showing things that have newer versions first. And this just makes sense because you not only give better instrumentation, but just in general, newer data tends to be better. So these were sort of low-hanging fruit that we could implement easily, and hopefully it will make a big improvement. Another one that we implemented, I don't know if Chris mentioned this, but just as a heuristic, we implemented an improvement where collections with granules show up higher in the list of return results. Because generally, people actually want something that has granule data. Another big improvement we made was we implemented something in the CMR called humanizers. Humanizers are implemented to as a way of providing standardized fields in the metadata. Again, we talked about the metadata having issues with regards to misspellings or just inconsistencies in the way things are labeled. And actually change the metadata. We still store the original metadata in the CMR, and we still return the original metadata when people ask for it. But this provides extra fields that are indexed within the CMR in a consistent way. And an Earth Data Search client can take advantage of this to provide improved facets. So you can see here on the left we have biosphere and biosphere are two different facets that came back with the older version. Now they're all mapped to biosphere. So there's a humanizer that says that biosphere should be mapped to biosphere. We have spectral engineering, two different ways of, with a slash and without a slash at the bottom. They're mapped to a consistent spectral slash engineering. So now we have one facet as opposed to two. So just small improvements like that have made, make a pretty big difference. We still have issues with relevance. With regard to faceting. Just the sheer number of things means that we can still have categories to get buried by other categories simply based on the number of results that are returned. And we are working on that, but it's still an issue. We have made interface updates to Earth Data Search. In particular, you can choose how you want to sort based on relevancy as opposed to some of the other, based on temporal or some of the other things. And just general improvements to try and take advantage of some of the things we've done in the CMR. Okay, so how do we measure our success here? How do we know whether or not these are actually making, these are making improvements for us? First of all, there are definitely challenges associated with metricing your relevancy. We don't have a gold standard yet that says, of our holdings, these are the things that show up first. And it's kind of hard to do that anyway because different people want different things. And so it's hard to say this is the absolute standard by which it should be returned. In addition to that, we have a relatively small population of users. And so the statistics we develop can be limited with regard to that small sample size. Also, definitions of success in a free site are different than what you would define if you were Amazon or even Google, where you're looking, you're looking strictly based on number of sales. So it's a little hard to define what success means here. But in general, I think what Chris said about returning the information that people actually want is it's a little bit more nebulous than the amount of product we sold, but it's an important measure to try and achieve. The last thing is that you have an issue of the tail wagging the dog, which is to say, it's possible if we define what should be the most relevant results, that simply by showing them, almost exclusively, we make that happen. So people can only get what they can see, and so therefore, if you say this is the only thing that people are going to be able to see, then you sort of fulfill that yourself. That's what they see. However, we still hope to improve what people are actually getting, and so we can look at some of the numbers that we've come up with to measure that. The first thing is we've established use cases and certain usage goals within the Earth Data Search that we can measure how often people using metricing within the client itself. We can measure how often people have reached those goals, which would be things like spending 5 minutes within a session, sticking around, basically. Visits that end up in someone actually acquiring their data, going to a download page or setting up an order. How many times people actually access their data or complete that acquisition. And we can see that if you look at this graphs on the top, you see basically a slight uptick towards the right, basically 20% of these graphs. Let me try again to see if we can get the mouse pointer to move. Okay, so basically right around in here is when we started implementing. This is right around October, I think, of last year, is when we started implementing these new heuristics and these new relevancy improvements. And so you see a slight uptick there. It's not huge, but it is visible. A little more obvious here is if you look at the average search rank of access data, which is to say a list of search results to people the data they actually follow through with. In October of 2016, it was 5.8. So in other words, about the sixth item in the list of things that were returned was the one that people seem to be looking for because it's the one they actually downloaded or went for. And we see a slow but small but steady improvement throughout the months after having implemented these relevancy improvements. So now the average search rank of access data is around 4.2. So it's basically about a 20% or 25% improvement in terms of the position in the search results of the what people were actually looking for. Oops. Okay, well, that's it, Jacek. That's it for me. Thank you.
As I mentioned, we have a little search relevancy group, working group that we've been running within NASA. And one of our guys reached out to Stefano and had him give a talk on the GeoDAB project that he's been working on. And although there were some overlaps in approach, there were also some fairly different aspects to Stefano's approach. So I thought it would be particularly useful to have Stefano come in and give the GeoDAB approach on this to sort of compare and contrast with what we've been doing at NASA. So Stefano, please take it away.
Yeah, thank you very much, Chris. And yeah, indeed, we have developed this brokering framework in the GEOS initiative. I'm sure that you know about GEOS, the Global Earth Observation System of Systems. And you know, I mean, this is what is commonly showed in terms of the general environment or ecosystem of the GEOS. And as you can see here, we have an upstream, a midstream, and a downstream side for the ecosystem. And many GEOS data providers share their data system, their data, infrastructure. And indeed, there are also very complex federation systems such as CEOS, but also other WMO, etc. But also very simple or small data systems. And so we have this plethora of heterogeneous sources, as also Chris explained. This is one of these of big data. So we decided to harmonize as much as possible, as far as possible, of course, these different metadata content and use this let's say harmonized view in order to perform a discovery. And since we have so many sources, we ended up, as also Chris explained, with many possible matching result set elements. So, for instance, here we have something like 40 discoverable and hopefully accessible million data set. And at the granular level, at the file level here, we have something roughly about 200 million. So it is clear that we needed, as also Chris said, a strategy. And this strategy is, of course, ranking and pagination strategy. And today, I'm particularly focusing on this topic. We also implemented other, other approaches in order to improve discoverability, such as result set refining by filtering, a two-step query, etc. But today I would like to tell you more about what is our ranking and therefore a pagination strategy, and I will explain our ranking scheme. We use what is called weighted quality scores approach. So we define a set of scores, and then we weight these scores so that this metric is configurable. So you can change the weights, and so you can give more importance to different quality aspects rather than others. We have two types of scores, static and dynamic scores. Static, of course, means that they are pre-calculated in a batch way, and they are based on the quality of metadata, on the real accessibility, etc. While dynamic score is comprised of calculated on the fly goodness in terms of matching the query constraints. And so let's start with the static score. As you can see here, we have 4 different quality elements. The first one is the metadata quality. I will cover each of them. The other one is the essential variable quality. Essential variables means that some variables are considered by our users more important than others for a given scope. So let's take, for instance, the Sustainable Development Goals for calculating one or more specific indicators. Some variables are considered more important than others. So here we can have a list of essential variables, and if these matching record is providing access to what is an essential variable, here we have a sort of quality, score. Then we have another GISS concept, which is the GISS data core quality. GISS data core in GISS terminology means fully open and free. So if the data set, if the data is fully open and free, then once more here we have a certain plus. And then the access quality. Some of these scores are very easy. For example, these essential variable and GISS data core quality is a weighted Boolean, indicator. So it is true or not, and we can give a certain weight. Some others are a bit more complex. For example, here we have the metadata quality score. The metadata quality score is calculated by considering how complete is the metadata of the data set, of the record here. And in particular, we considered both discovery and access metadata element. So for the discovery, very simple elements such as a file identifier, the abstract, the spatial extent, the time extent, and title. So if these elements are present, we have a certain sum. If they are not present, of course, the part of the score is decreasing. And for access metadata element, we are checking if the data set is directly downloadable, and if this is supported, not just the download of the entire data set, but it is also possible to download specific layers or variables contained in the data set. Or in other cases, if we don't know much about what is going to get downloaded, it's just a direct link, such as an FTP or an HTTP, and the final minimum level for accessibility here, it is a landing page. So it's not directly downloadable, the data set itself, but you can land in a web page and then through this page access data. So this is how we generate this metadata quality score. And then since GISS recently is moving more and more into accessibility, so from discoverability to actual accessibility, we also have an access, a very dedicated access quality score here. That basically means that we are checking whether this data set, this potential matching data set is really downloadable, if it is coming in a format that can be transformed in order to generate a different encoding, or in order to change some of its aspects, such as the coordinate reference system, or if we are able to, subset, etc. And the final feature that we consider, it is whether this dataset is coming or not with a preview. In a particular, if we have tiles, or we can use tile in order to, visualize quickly, visualize this data set. So these, all these aspects are considered in order to generate this access quality score. And then there is the dynamic part, of course, that basically means how well the query constraints are satisfied. And in this case, we are considering a query using a set of textual terms plus a special constraint, so a bounding box. We are not considering a temporal extent for ranking. Of course, I mean, you can use all these elements in order to, specify clauses, query clauses, constraints. But for ranking, we are not considering the time period, because it is not one of the most used clause. So we observe that generally queries come by keywords or textual terms and the bounding box. And so we generated this very specific score. And in terms of textual terms, we are matching, and we provide a goodness index for how these are matched in the title and or in the abstract element and or in the keywords or in any other textual elements. So we can match these textual clause by title or by abstract or by keywords or any other, and we can give different weight, different importance to each of these matches. And this is my final slide. As far as the bounding box, of course, here we consider whether or not the record bounding box is contained into the query spatial extent clause. And we also, as you can see by the formula, we also try to give a sort of fitness score in terms of how well is contained into this spatial extent score. So this is as we are presently generated the ranking, and according to this ranking, of course, we have pagination approach. So you may define how long is a page, so you can define a number of entries for each page. Commonly, by default, we have 10 matching records for each page. And yeah, I mean, this is what I wanted to say today. As I said, we have also implemented other strategies, but I guess that this is at least the first strategy set up in order to address this common issue, how to give a relevant answer to potentially a quite generic query. Thank you for your attention.
Okay. Thank you very much, Stefano. Now moving forward, looking forward in this topic, Chris and Stefano will conclude our presentation part of this, and then be sure to start typing your questions into the Q&A box so that we could answer the questions at the end. Chris?
Thanks, Ansuk. I just want to go through a few slides, really more to remind myself of what I wanted to touch on with respect to looking towards the future here. And most of the, in fact, almost all of the heuristics that I showed in the first part of the talk were sort of independent of the user. You know, it was really a property of the intersection of the search terms that were put in and the metadata of the actual data set. But we should be able to do much better if we can understand a little bit more about the usage or about the usage that the particular user is going to put to it. So we mentioned the community usage heuristic, and right now what we have implemented is really just the entire community. So in other words, it's the whole group of users, which users are using more. But we've also recently implemented a user profile capability that allows us to fractionate the users into different disciplines or different types of users. And so we have some hope in the future of making that a little bit more user community specific. So for instance, if I'm an atmospheric scientist, perhaps what I'm looking for in terms of temperature is different than if I am an oceanographer, for example. And so we might have different community usage scores for the different communities that a user might be part of. But it's still, you know, I don't know how well this is going to work because, you know, as James mentioned, we've got a fairly large group of users from the standpoint of the number of folks using space data or space-borne Earth observation data. But it's, you know, statistically, we don't know if it's great enough to support too much fractionation of those communities. We'd like to go even further if we could, and that is to somehow guess at the user's intent. And here again, we're kind of going back to their declared interest in their user profile. We might be able to also tell by hints they give us in the search terms. But here's an example, for instance, where if we're serving an application user, they prefer higher spatial resolution and near real time, versus a climate modeler doesn't really care about either one of those. You know, most of the climate modelers today are actually working with low resolution data spatially, and the near real time aspect isn't even an issue. Meanwhile, if you look at that middle category of students, you know, we could send them these very sophisticated, you know, HDF, you know, unstructured grid data sets. But if they can't use them, they're really of no use whatsoever to the students. And so they might be happy just in getting the data sets that are fairly simple level 3 grids in nicely, an easy-to-use format like NetCDF. If we look even further out, you know, that community usage is one thing, but we'd like to even be able to gauge what impact has a data set had on the community using it. And so here's a case where we could look at the articles written about the data, or the applications using the data, or the educational uses, the curricula that have been developed from that data, and say, well, you know, for instance, this data set has many more articles than this other data set, and therefore it's more likely to be of use for your research use. And we could even go, you know, further than that and look at, for instance, the H-index of a data set. Now the data sets are beginning to be cited in the reference section more and more often. Now, one of the things I like about these kinds of seminars, the kind that we're having today, or got more than one approach being shown, is that I see brand new approaches. And so there was a search relevancy session at AGU, the one where I gave my first talk, and James gave a similar version of that talk. But during that session, there were a couple of other interesting approaches that I hadn't even considered, and they had to do with machine learning the relevance. So that it's basically saying, if you've got enough queries and results, that you might be able to simply have your algorithm learn using deep learning techniques, multi-layer neural networks, which criteria for which data sets are then map into some user expression of whether they got the right answer or not, whether they downloaded it, for instance. And so this, of course, will require a lot of data, a lot of statistics for us to make this work. It might even be the kind of thing where we couldn't get it to work on our own, but perhaps, if we were to pool the resources, the relevancy metrics, for instance, from, say, GeoDAB with the WGISS, perhaps then we might actually be able to, make our algorithms stronger than they would be individually. So that's kind of where I would like to go. Whether we can go, how fruitful that will be is perhaps in question. But now I'd like to ask Stefano if he'd also like to have any thoughts on where to go in the future. Stefano?
Yeah, thank you. Well, I guess that we have a similar, at least some similar visions. Indeed, I mean, I think that here we can have a twofold, approach. One is to develop a more specialized interfaces in order to serve the specific communities, and this in GEOS started this activity, started, for example, by including what are called community portals. So not just one general portal, since GEOS is really multi-disciplinary, but it is also now, a part of the GEOS ecosystem, are now also considered community portals. So one of the objectives of this community portal is to provide more specialized discoverability. That basically means, some of the aspects that you touch. So to, for instance, include very specific facets, discovery facets for specific targeted users. For instance, we have experimented with sentinel data. We know that very expert users are looking for a specific data set, not only by title or keywords or bounding box, but also because they are interested in data sets that are, don't have a crowd coverage level and so on. So that's one possible advancement. The other one, it is indeed to contextualize data set in a more general, usage framework. So we need more knowledge, we need more semantics here, and so not just data, discovery data, because you have some query clauses and you match these clauses with some metadata elements, but also because you ask your user to tell you what is their issue, what is their challenge, what is the use case, what is the topic they are interested in. And then from this knowledge, you can understand more what kind of data set they are really looking for. And of course, you can, guide them to, discover data set. So not just one step query, maybe it's a more a more elaborated query phase, but definitely we experience that we need to include some knowledge into the present discovery process. My last, and I think that along, in keeping with this approach, we also envision to set up a sort of social, social functionality, so to allow users to provide feedbacks and or tags. So when they use a data set or they discover and then use a data set to provide some tags, some feedbacks in order to capture this knowledge, how they use this data and how this data is fit for particular purposes, so that we can reuse these in order to satisfy other user needs. Thank you.
Okay, now we're to the question and answer session. Jennifer, I'll turn that over to you.
Okay, thank you, Jan-Suk. Can everybody hear me okay?
Yes.
My name is Jennifer Brennan. I'm the communications lead for ESDIS, and I will be moderating today's question and answer period. Our first question is, are all data sets in the MIM database included in the search?
I think that's probably one for Stefano.
Sorry, I mean, are all the MEM data set? What do you mean with sorry, MEM data set?
This is Andy. Maybe I can help out here too. The MEM is the CIOS Mission Instrument Measurement Database. So Tom, we actually are meeting with, we being, earlier it was mentioned about the CMR, the Common Metadata Repository. So we've been speaking with George Dyke and Stephen Ward on creating a metadata model that can help the MEM using the information that we're providing inside of the CMR. So that topic is going to come up at the next CIOS SIT meeting in April. I just spoke to them actually last week about this to try to combine the metadata records from the two repositories.
Yeah, I see.
We would.
Please go on.
Oh, no, sorry. I was going to hand it over to you, Stefano.
Okay. Yeah, no, sure. I mean, we had a dedicated meeting with our WGISS and quick colleagues about the process and the brokering process. And indeed, I mean, what we have been doing with the Global Master Directory, GCMD, we are going to do with the CMR, so the SMR. So we will harvest periodically the content of this catalog, and we will broker the entries of these the entries and the new entries of these catalog, and we will use the WGISS interface. We discuss about which APIs is better to use and at what level we will arrive with our harvesting. With Jan-Suk and other colleagues, we discuss these aspects as well as what is the best reharvesting time. So indeed, I mean, we need to advance the current brokering approach because things are changing from both sides, of course, and they are getting more and more, more and more exciting, and so we can do better. And we have started a sort of roadmap in order to accomplish more in terms of interoperability. So I guess that we are not now harvesting the new catalog, but this is going to be very soon.
Okay, thank you, Andy, and thank you, Stefano. Our next question is, how are heuristics affected by machine-based queries? queries that are possibly broad and frequent without a specific research question behind it?
Yeah, I mean, I can try to say something here. Yeah, indeed. I mean, this is what I tried to mention, before in terms of future, not in terms of present discoverability. And indeed, I mean, we need this, this kind of knowledge conceptual, framework where we link concepts, in particular these more general concepts and studies or challenges or big questions. I mean, these are the concepts that we need to capture, formalize, and link these concepts with actual artifacts. And among these artifacts, indeed, data set are there. Not only, of course, the data set. We can have, publications, we can have documents, we can have other kind of products and even knowledge bodies. But data set indeed should be part of these, let's say, conceptual or knowledge framework. It's not easy. I mean, in GISS, we have started, some people of GISS, part of GISS, I've started thinking about that. It was called, GISS knowledge base, but anyway, doesn't matter what is the name and what is the label here. What is, important is the need. There is this need, and I think that this is a part of a possible future advancement for improving discoverability. Chris, do you want to?
Yeah, so on the heuristic side, that is a really interesting question. Hadn't even really considered it until now. The thing is that even those machine-based queries, they may have a particular purpose behind it. Some of them might be more of a discipline-specific kind of query. Others might be, really super broad, basically give me everything you have. And I think in the latter case, what we're inclined to do is to enable sort of broad-scale harvesting to be a little bit easier. And so then, in a sense, it doesn't quite mix with the other search and query results that are coming from actual people with a research goal. So I think the trick is to kind of keep those separate with respect to trying to figure out what the purpose is of a particular query client.
Okay, thank you, Chris. Are there any additional questions? While we're waiting to see if there are any additional questions, I wanted to point out to all of you that today's presentation files are available to download. Located in the lower right-hand corner of your screen, you will see a file sharing pod. If you click on any of those files, you should be prompted with an option to download those files. Okay, let's see here. Are there any additional questions?
Okay, thank you very much, Jennifer, and thank you to our presenters. Thank you for Chris for organizing this really interesting session. We have recorded this, and this will be available through the WGISS Tech Expo web pages, the link to the YouTube recording. Really appreciate everyone joining, and I think this will get replayed many times in the future.
Thank you very much for having invited me.
Thank you.
Thank you, and thank you to everybody that either stayed up late or got up early to be part of this.
Yes.
Thank you.
Thanks very much.
Bye.
Stay tuned for the next Tech Expo webinar topic. All right, coming up in a couple months. Bye.
Bye, everybody.
Goodbye.